Welcome back to the AI Research Roundup. I'm your host, Alex. Today we're diving into DDT, Decoupled Diffusion Transformer, published April 8th, 2025. So, current diffusion transformers. These are AI models that create images by gradually refining noise through many denoising steps, often face a dilemma. They use the same modules to understand image's core meaning, its low-frequency semantic component, and to add fine details, the high-frequency components. This paper introduces the Decoupled Diffusion Transformer, or DDT, which separates these jobs. This leads to faster training and better image quality, achieving excellent FID scores. FID, or Fréchet Inception Distance, just measures how realistic the generated images are. And it's always great when researchers share their work openly. The code for this Decoupled Diffusion Transformer is available on GitHub. You'll find the source code, configuration files, and scripts for training and running the model. They even include pre-trained checkpoints, which are like saved versions of the trained AI, and a little demo app. Alright, so figure 1 here really helps visualize what's going on. On the left, in panel A, we see the architecture of their Decoupled Diffusion Transformer. It has two main parts: a condition encoder, which processes the noisy image data, the current time step in the denoising process, and a class label, and then a velocity decoder, which uses that information to predict how the image should change. This is different from panel B, a conventional diffusion transformer, which uses a single, combined module. Then, panel C shows a performance comparison. It plots the Fréchet Inception Distance. Remember, lower is better, against training epochs. A training epoch, well, that's just one full pass of all the training data through the model. And you can see their Decoupled Diffusion Transformer, the DDTXL/2 model, achieves a really good low Fréchet Inception Distance with significantly fewer training epochs than other models like RIPA, about 4 times faster, which is quite impressive. Alright, and figure 3 here gives us a great visual of that reverse diffusion process we've been discussing. It shows how images, like the spider and the bird examples, are actually generated. You can see them starting out quite blurry, representing the initial low-frequency information, and then, as the process unfolds over time, denoted by T, those high-frequency details really start to emerge. This makes the images progressively sharper and clearer, with the model spending more effort on these finer details as generation proceeds. Okay, so after seeing how the images are built up, figure 2 here shows us the impressive end results. These are selected high-resolution image samples generated by the DDTXL/2 model, which is a specific version of the Decoupled Diffusion Transformer we've been discussing. The images were generated after training on ImageNet. That's a massive standard dataset of labeled images used to train and test AI. You can see examples at both 256 by 256 and 512 by 512 resolution. And they're really quite detailed, from the red panda to the butterfly and even the landscape. These were generated with CFG, or classifier-free guidance, set to 4.0. Classifier-free guidance is a technique that helps improve the quality and relevance of generated images by steering the generation process without needing an extra classifier model. So, Table 1 here really quantifies those impressive results, specifically for generating images on the ImageNet 256 by 256 dataset. It compares different models, including the Decoupled Diffusion Transformer, looking at metrics like Fréchet Inception Distance, which we know lower is better, and also Inception Score, or IS. Inception Score, well, that measures both how good individual images are and how diverse the set of generated images is, so higher is better there. The table shows results both with and without that classifier-free guidance. And with classifier-free guidance, the DDTXL/2 model achieves a Fréchet Inception Distance of just 1.31 after only 256 training epochs. Even without classifier-free guidance, it achieves a strong 6.62 Fréchet Inception Distance in just 80 epochs. Okay, moving on to Table 2. This table digs a bit deeper into performance metrics, specifically after 400,000 training steps and, importantly, without using that classifier-free guidance we just talked about. It compares different sizes of the decoupled diffusion transformer model, like B/2, L/2, and XL/2, against other baseline models. We're still looking at Fréchet inception distance and inception score, but this table also introduces precision, which tells us how realistic the generated images are, and recall, which measures the diversity of images the model can create. Across all model sizes, the decoupled diffusion transformer models consistently show better Fréchet inception distance and higher inception score, precision, and recall values than their counterparts. For instance, the DDT-XL/2 model achieves a Fréchet inception distance of 6.62 and an inception score of 135.1, outperforming the improved RIPA-XL/2. Alright, so Figure 5 gives us a visual on why the decoupled diffusion transformer can be made more efficient during the image generation process. This heat map shows the cosine similarity, which is basically a way to measure how alike two things are, in this case, the self-conditioned features from the encoder, across different time steps. Time steps, remember, represent the progression of the generation process from noise to a clear image. The brighter colors, especially along the main diagonal and close to it, indicate very high similarity, often above 0.8 or even 0.9. This strong correlation between adjacent steps means there's redundancy. The information isn't changing drastically from one tiny step to the next. So that redundancy we saw in Figure 5, that's what allows the decoupled diffusion transformer to speed up inference by sharing those self-conditioned features. Now, Table 3 shifts our focus to a higher resolution, ImageNet 512 by 512. It benchmarks class-conditional image generation, meaning the model generates images based on specific class labels. We're looking at Fréchet inception distance, SFID, which is a spatial Fréchet inception distance, a variant that also considers spatial features in images, inception score, precision, and recall. The decoupled diffusion transformer XL/2 model, after 500,000 training steps and using classifier-free guidance of 3.0, achieves a remarkable Fréchet inception distance of 1.28 and an inception score of 305.1, outperforming all other listed models. Those results on high-resolution ImageNet are pretty striking, aren't they? So, to wrap up, the decoupled diffusion transformer really stands out for its innovative architecture. Separating that self-conditioned encoder allows for much better image quality and faster generation. This work is a big step forward for creating highly detailed images more efficiently. Thanks for tuning in to this AI Research Roundup. I'm Alex, and I'll catch you next time.